but as we shall see that they can save considerable amount of energies. So, let us see. So, now let us look at what happens to the operating characteristics when you have damper control. So, here is the fan curve, you can see that. Now, a damper is essentially actually puts a resistance. So, basically we had this. So, you can consider the damper to be part of the load. So, as you are closing the damper, this load characteristic of P equal to k q square, this k value is gradually increasing, which means that as the damper is closing, more and more pressure is required to drive a given flow, that is natural. So, as the damper is closing, this curve is shifting this way, because this is increasing k. Now, what is happening to the energy? The energy in a fan, the energy being delivered is P into Q. So, in other words, it is the area of this rectangle at any operating point. At this operating point, it is the area of this rectangle. This is the area. When you are at this operating point number 2, then this is the, actually I could have taken a different color. Okay, let me take this color. So, at the other operating point, this is the, and when you take the third operating point, which is this, then this is the area, energy demand. Okay. So, you can very well see that what is the difference, how if you move from this operating point to this operating point, what is the difference in energy? The difference in energy is actually this part is common, this part is common between them. Can you see that? So, this is common. So, this is gone. On the other hand, this is gone and this is added. So, the energy saving is actually comes down to the difference between this area A1 and this area A2, which is very low. So, you see that even if you have moved from this operating point, you have come from 100% to 80% flow, the energy has not fallen by that much amount, the energy has fallen only by the amount of difference between these two areas, right. In fact, the same, so the energy fall is not so much. So, in fact, if you can see the energy curve. So, you see that in damper control, as you are going from 100 to 80, the energy fall is only this much, very low. So, you have, so there is a 20% flow reduction, but there is probably a 5% energy reduction, power reduction. This is not pressure, this is power, this is wrong. Okay. So, that is why this method is not so energy efficient. You are not saving energy, flow is reducing, but you are not flowing energy. But it is a very simple method, you do not require much, you require either a valve or a damper and you close and open it. Now, what happens if you do a variable speed drive? Now, this is that particular case. So, if you want to see this, we can come to, we can let us come to the, if you want to see this figure. So, what does it say? It says that for our example and for the fan curve that we have seen, If you take 100% CFM, 100% flow, the horsepower requirement becomes 35. We will see how it comes to 35 from those curves. If you have 80%, the horsepower requirement is also 35, hardly any reduction. If you have 60%, it falls to 31, if you have 40%, it falls to 27. And from the load characteristics, we have seen that 100% load stays 10% time. So, per hour, per percent is 3.5 is the weighted horsepower. Oops. So, 35 horsepower level stays 10% of the time. So, therefore, weighted horsepower is 3.5. We are trying to calculate the average horsepower, right. Similarly, 35%, again 35 stays 40% of the time, that is 14, then 31 stays 40% of the time, that is 12.4, and 27 stays 10% of the time, that is 2.7. So, the average horsepower requirement is 32.6. Remember this figure. We will come back and see that if you do a variable speed drive, what for the same pump and for the same load profile, if we had a variable speed drive, what would have been this figure. So, we have a 32.6 horsepower average horsepower requirement for the load and the pump, right. So, just we would also like to see how these 35, 35 and 31 figures are located, because otherwise you may not believe me. So, let us go back and oops, okay. How do we close this? Okay. Can I go back to the so I am going back to the fan curve just to show you, all right. Yeah. So, we are at the fan curve. So, let us see that actually this has been calculated with a fan RPM of about 300. So, this is the 300 curve. So, we are looking at this curve, this is the constant RPM 300 curve, okay, and we are at 100%, okay. So, this is somewhere over here. So, you see that it is somewhere over here, can you see that? So, it is somewhere over here, okay. Now, you see what is the power requirement here, look at these curves, this is 30, this is the constant 30 curve, this is the constant 40 curve, 40 horsepower. So, where are we? We are at 35. Now, what happens when you are 80% flow, that is when you are here. So, when you are here, you are roughly here. So, you are at 80% curve. Now, you see that where are you? This curve and this curve are moving in parallel. So, if it is 35 here, it is going to be 35 here also. That is why this is also 35. This is also 35. If you do 60%, that is here, where are you? You are 60% would be somewhere over here. Yeah. So, you are here. So, that is a little reduced. You see, this is the 30 curve, this is the 40 curve, this is the 40 curve. So, therefore, and this it is actually a nonlinear variation, because 50 to 60, 60 to 70 it is gradually getting closer. So, this is something like 31, 32, it is slightly reduced actually. So, this is how you get those figures from an actual pump characteristics. Okay. So, now we go forward quickly again and go on to the variable speed drive case and see what happens, right. So, that is the case. Now, here before we discuss that, we need to understand what are known as the fan laws. So, what are the fan laws? The fan laws say that in a fan roughly Q2 by Q1 equal to N2 by N1. If you operate, if you change the speed, the curve shifts in such a manner that on the q axis you are going to get proportional these things, and P2 by P1 equal to N2 by N1 square. So, the horsepower variations are going to be N2 by going to vary as N2 by N1 cube. So, similarly, so if you know if you know this Q2 by Q1 and you know P1, you can calculate P2 by this formula, because P2 by P1 equal to Q2 by Q1 whole square. If you eliminate n and n from these two, then you get basically P2 by Q2 square equal to P1 by Q1 square, right. So, P2 by Q2 square is equal to P1 by Q1 square. This is at speed n2 and these two are at speed n2 and these two are at speed n1. Okay. So, now having known that, we come back right. So, we see this variable speed fan control. So, now what happens is that if you want to reduce the speed, we are not going to put any damper or any valve. In other words, the characteristic of the system remains unchanged. Now, we are changing the speed of the fan. So, the fan characteristic shifts. So, this is let us say N1, this is N2 and this is N3 and N1 is greater than N2 is greater than N3. Okay. So, now what happens is that now the operating point will change along this is the first one, then this is the second one and this is the third one. So, what happens to the power requirements now? So, the power requirement for the last one is this. See, previously as we were reducing flow, pressure was going up. So, the power was not falling. Now, as we are reducing the speed, it is not just that the flow is reducing, it is the pressure is also falling, right, and very rapidly too. So, what happens? So, this is the area required, this is the energy, and similarly for this case second operating point, this is the energy, and for the third operating point this is the energy. So, for the third operating point this is the energy. So, you can very well understand that energy falls very sharply. So, that is why you are going to get a huge benefit in terms of energy savings, right. So, you can now see that the power curve how sharply it falls compared to what you had seen in the case of the outlet damper control. So, this is the essence of energy. So, this shows that how energy saving variable speed drive can be, and just to drive the point home, we are going to show you that we are just applying that same formula that what happens is that, remember that at Q1 equal to 100 we had a HP requirement of 35 HP. So, with Q1 equal to 80, Q2 equal to 80, HP requirement will be 35 into 0.8 whole cube, which is equal to 35 into 0.512, which is almost equal to 18 horsepower. So, this is 18. Similarly, if you multiply this by 0.6 whole cube, then you will get 7.56, similarly 2.24. So, these are the horsepower requirements now applying the fan laws, and you can get very similar figures if you see the fan curves, because the fan curves obey the fan laws, right. So, here we are. So, now let us see the energy average horsepower requirements when you are varying the speed. The 100% case is the same 33.5, the 80% case is now totally different. This was 35, remember, this was 31 and this was 27. So, now the average horsepower requirement is 32, where the previous one 13, the previous one was some 32 point something. So, you can imagine that what amount of power saving has been achieved, almost 20 horsepower, which is 1400 kilowatts, right. 14,000. So, yeah. So, this is this is a little calculation, this is this dollar figure is because of the source from which this is taken, but this turns out to be almost equivalent to hours. If you take about 45 rupees per dollar, so this becomes about 2.5 rupees, which is a kind of an average rate, not exactly, it varies from state to state, it varies on various energy slabs, and industrial energy rates are anyway not just depends on the kilowatt, it also depends on the maximum demand. So, approximately speaking, if you take 2.5 rupees and if you take 2.5 rupees here, then you can inquire roughly you have a 10,000 kilowatt hour per month, 10,000 kilowatt hour per month saving at 2.5 rupees per kilowatt hour, that comes to be a 25,000 rupees saving per month on a single fan. Now, the question is whether this is justified. So, whether it is justified will depend on, see, apart from the conservational aspect of energy, that we need to be energy efficient, we need to because fossil fuel is not going to last forever, etc., etc. If you ignore those things, then people are going to look at money. So, if you, it all depends on it, it's again remember that in the early lessons of the course we talked about capital cost and we talked about variable cost. So, energy is variable cost. So, whether people are going to resort to simple damper type of control, or whether they will actually buy these variable speed drives, depends on how much money is required to buy these drives and how much money is required to maintain them against how much savings these drives give. So, it is all basically because of these comparative figures which will decide practically speaking whether a particular industry is going to adopt this technology or the other. Now, it so happens that why the outlet damper technology was more common is because the variable speed drive technology was not so developed, it was not so robust. So, it was way too expensive. So, therefore, people always opted, even if they were not energy efficient, people opted for this damper and valve control kind of techniques. But now with these variable speed drives really becoming robust and cost effective, it shows that it makes a lot of sense to acquire variable speed drives for such equipment. Okay. So, basically it is the cost and it is the capital cost of purchasing the equipment and the cost of maintenance which decide whether these technologies are going to be adapted, right. So, you see this shows that how important it is to make a technology cheap and to make a technology robust, right, otherwise it is not going to be adopted. So, we move over to the case of pumps. For pumps, this is a pump characteristic, again the same thing, basically same thing. So, we are going to do this little bit fast. So, this is the pump characteristic and this is the system curve, which is again, of course, there is a little difference in the sense that fans drive gases which are compressible and pumps drive liquids which are generally incompressible. So, there is a slight difference there, but it looks essentially the principle is all the same. This side you have total head in feet of water, right. Previously you had inches because that was gas, this is liquid, and you have this is given in you have to choose a unit because this is from an American reference. So, this is gallons per minute. So, similar to the fan characteristic, you can have a pump characteristic where again you have the pressure up. I made a mistake. How do we go back now? We do not have. Oops. Okay, so this is going to be tricky now. Oops, I can do this. Yeah. So, yep. So, again you have this pressure and this side you have flow and this side you have various RPM. You see that so you have this constant horsepower lines and the various speeds also. So, you see that there are this constant, these lines are these various speed lines and these dotted lines as before are these dotted lines are the constant power lines. So, it is like the old curve itself. Okay. So, again in this case in the case of fans you put dampers, in the case of pumps you put valves, right, flow control valves, which we have already seen in our earlier lesson. So, that kind of when you close the valve it is generally called throttling, right. So, this shows how the operating point shifts if you have one system which is open, another system which is throttled. So, again you see that the load curve changes and the operating points will shift from this to this, right. So, the same thing happens here again for pumps. This is a variable speed pump control. So, you have a constant speed drive. One way of controlling is either you have a constant speed motor drive and you have a valve, or you have a variable speed drive of the pump depending on the feedback, depending on the load. Basically that drive has to be controlled and some speed reference has to be given. We will see in our future lectures as in detail as to how the speed of a motor and a pump can be controlled. Oops. Okay, next. Now, if we control the speed as before, the pump characteristic will now come down. This is N1, this is N2 and N1 is greater than N2. So, the operating points will now shift from this to this, okay, just like previous case. So, if you do a similar analysis on this pump, a similar thing comes out, that is, see at 1200 the head requirement is and the BHP requirement is 25, 25. At 960 for throttling it is 23, hardly reduced, but for variable speed drive it is much more reduced, again because of the fan and the pump laws. Okay. So, a similar saving will result, that is what. So, we come back. So, this is just another depiction that if you have it shows that if you had a throttling method, then the energy would have fallen along this path. if you have variable speed method, it will fall along this path. So, this is the energy saving that you are getting, right, or rather these at any load, this is the energy saving that you are getting. There is a difference between these two, which is substantial. So, only thing is that in the case of the pump, there is sometimes pumps operate with a static head. So, if you have a static head, then the load characteristic can be, this is one without static head, where P is equal to k q square type of characteristic, but a pump can also operate with a static head, where the characteristic is P equal to k 1 q square plus k 2. So, this k 2 is the static pressure which is there at the pump inlet. Sometimes the pump may be elevated, you know. So, in such a case it has a for example, the load, the pump may be below and the load may be at a vertical height. So, even if there is no flow, there is always a constant pressure on the pump. Okay. So, for driving such loads, as we shall see, that the energy saving is reduced. So, it turns out that with static head, this is the throttling method. So, and this is the variable speed drive method with no head. Okay. This is for 31% head, this is with 63% head. So, as the head increases, the energy saving actually reduces and moves towards the throttling method. Anyway, those are fine points. So, what we have done in this lesson is that we have seen the fan and the pump characteristics, we have seen the load characteristics and typical load profiles, and we have seen two kinds of control, for fans outlet damper and for pumps throttling control, and for pumps and fans we have seen the variable speed control, and we have seen the energy characteristics of these control schemes, and we have got an idea of the energy savings, right. So, here are a few questions for you. Why is it that typically load requirements are stated in terms of flow rates? Why? You have to look at the applications, and we have discussed this. Why is it that load requirements are generally shown as parabolic pressure flow characteristics? Again, and third is that from these characteristics, it will be interesting if you can find how the efficiency varies. Does it increase, does it decrease as flow is reduced? So, these are a few questions on which you can ponder, and thank you very much.